Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Rocks, Fossils and Time part 2. Okay, so in the previous video we've been discussing fossils, how they form, the different types of fossils and what we really want in a fossil in terms of, being helpful to a geologist. So now we need to have a think about how fossils are useful in terms of relative time. So the usefulness of fossils as a means to match strata of similar ages was first noted by William Strata Smith. I should point out that there were actually earlier examples of this, so Leonardo da Vinci actually made a similar comment, but in terms of actually applying it to rocks on a large scale, William Strata Smith was arguably the first person to actually do so. So, as he travelled around the United Kingdom, surveying, doing surveying work for canal building, mining, quarrying companies, he took notes of the rocks and the fossils that he saw as he was going around. So what Smith hypothesised was that if the oldest rocks are at the bottom of the sequence and the youngest rocks are at the top of the sequence, so that's the principle of superposition, the same must therefore apply to fossils. So if you have a sequence of fossils, the ones down at the bottom of that sequence will be the oldest and the ones at the top will be the youngest. He noticed that the sequence of fossils, especially groups of fossils that he saw, which were present at one locality, is consistent from area to area. So as he was going around, he would see the same groups of fossils occurring in rocks, and what he realised was that he could use these groups of fossils to actually correlate between those rock layers at different locations. He could use them as a way of saying, right, these rocks were clearly forming at the same time, even if they were, tens or hundreds of kilometres away. So what he had done is he'd therefore found a way to relatively date sedimentary rocks from different areas, just using the fossil assemblage. And his methods are still being used today by sedimentary geologists, so his technique still holds good. So his knowledge allowed him to accurately predict the fossil assemblage that would appear in rocks at a locality that he had not previously visited. So if he had some idea of what rocks, what the age of the rocks would be when he was going to a location, he could actually predict ahead of time what fossils he would be able to find. And this is very, very important because by doing so he was testing his idea. And because he got a positive result, he was backing up his idea and proving that his theory worked. So independently of Smith, Alexandre Bouguereau was making similar observations of the fossil succession around Paris. So his conclusions were the same, but his data set was a little bit more limited because he really stuck in the area around Paris, didn't really strike out into the whole of France to look for examples. So yes, same work, slightly different, slightly smaller data set. So the basic principle is that if we're starting off at location A and we see fossil X, Y and Z in our rock, so then we go to location B, we see fossil X, Y and Q. So the first question is are these rocks going to be the same age? Well, yes, fossil X is present, yes, fossil Y is present, but fossil Q is present at location B, so fossil Z is missing, and fossil Q isn't present at location A. So although they share two fossils, so they're probably of a similar age, they're not going to be of the same age. So what about location C? Well, at location C we have fossil X and fossil Y. Would that make location C the same as location A in terms of its age? The answer would also be no. Because yes, once again, we do have fossil X and we have fossil Y, but we're missing fossil Z. So just like location B, because you have X and Y, chances are location C is of a similar age to location A. So they're probably relatively close in age, but without fossil Z to definitively allow you to tie them together, you can't say they were forming at exactly the same time. What about location D? Well, at location D we have fossil X, fossil Y and fossil Z, just like we do at location A, so we can use that to say, right, these rocks were forming at the same time, they are contemporaneous with one another. So this is the very simple technique that William Strata Smith came up with, and it's, as you can see, it's very simple and it's highly applicable to geology even now. So obviously this then brings us on to the seventh of the methods of relative dating. So if you remember, we have superposition. That's the oldest rocks will be at the bottom of the sequence, youngest rocks at the top. Original horizontality. All layers of sediment are initially deposited as horizontal sheets, and therefore any tilting must have occurred after lithification. Lateral continuity, a layer of sedimentary rock will continue until it either thins and pinches out or hits some kind of vertical basin margin. Cross-cutting relationships, faults and dikes must be younger than the rocks which they cross-cut. Principle of inclusions, any inclusion within a rock must be older than the rock within which the inclusions occur. Baked contacts or contact zones, essentially any baked contact must be younger than the rock that is being affected, and therefore also what is doing the baking must also be younger than the rocks which are being affected. And then finally we have fossil succession, which is also sometimes called faunal succession. And this principle is relatively straightforward. It just states that fossil assemblages, so groups of fossils, succeed one another through time in a regular and determinable order. Very straightforward. All it's simply saying is if we find a fossil as a geologist, we can work out where it sits in the sequence, because we know the fossils occur in a set order. Geologists have spent hundreds of years now trying to get the fossils into the correct order, knowing when a fossil first appears and then disappears, so we know where they sit in time. And so as a geologist, as soon as you find a fossil and you can identify it, you know exactly where that fossil sits in geologic time, because the order is regular and determinable. So it's relatively straightforward. So all that's saying is if you find a fossil, you can work out when in geologic time it formed. So for every fossil, geologists get 2 data points. The first data point we get for a fossil is its time of first appearance, so when it first appears in the geologic record. And obviously we also get its time of last appearance, the last time it's seen in the geologic record. The majority of common organisms, especially shelly marine creatures, have very long histories, so they're actually relatively difficult to use for dating. So, there are some organisms, especially one of them in particular is called Lingula. It's a type of shellfish. It lives in sandy sediments and in beach and shallow water environments. That's been around for about the last 480 million years. So in terms of trying to date a rock, that's pretty bad, because you won't be able to know whether your rock formed 480 million years ago or last Tuesday. So there are some fossils which aren't good for dating rocks, but there are some fossils which are extremely helpful. And typically, the shorter the period of time during which a fossil existed, the better it is for dating rocks and correlating between rocks. So using a fossil assemblage, which means using more than one fossil, makes our lives a little bit easier. So we can use several different fossils as a reference point simultaneously. So this means that if we have an assemblage of fossils A, B and C, well, there's only a very limited portion of geologic time during which fossils A, B and C could possibly have coexisted together. So in this instance, what we can do is we can take fossils, even if they have these very, very long timescales during which they were present, we can still use those timescales and look for the point where they overlap, and that's also helpful to us. So sometimes we don't just rely on one fossil, we'll actually use multiple fossils to help date and correlate our rocks. So what about relative dating and the geologic timescale? Okay, so this is essentially, we're going to run through exactly how we got to the geologic timescale we have now. So between 1830 and 1842, naturalists, so these were early geologists, began to recognise bodies, my apologies, of distinctive rocks and fossils which they called systems. So you're thinking, okay, how did they decide what area they should include in one of these systems? Well, the answer is they just started. They just found a rock and they said, all right, we're going to start here, and then they would work their way up through the sequence, and they would stop pretty much where they wanted to stop. So essentially what they did is they went into an area, they found a package of rocks associated with that area, and that became the system. So a system is just the rocks. So during the 1830s, a gentleman called Adam Sedgwick studied the rocks of northern Wales and described what he called the Cambrian system. You might notice, by the way, Cambrian is also a name of one of the periods of the geologic timescale. At the same time, a gentleman called Sir Roderick Impey Murchison was doing the same thing to the rocks of southern Wales, and he termed that package of rocks the Silurian. Once again, you might notice Silurian is also a period on the geologic timescale. So what happened is so Sedgwick has essentially taken northern Wales, he's looked at all the rocks in northern Wales, and he's gone, right, I will put all of these rocks together and I will call them the Cambrian system. And at the same time, Impey Murchison down in southern Wales has done exactly the same thing. He's gone, right, I will take all these rocks here in southern Wales, I will bundle them together and call this the Silurian system. So as you can see, not exactly scientifically rigorous, but, that's what we're starting from. So when in 1835 their results were published, it was clear that the Silurian rocks were younger than the Cambrian rocks, so the Silurian rocks would sit above the Cambrian rocks in the relative timescale. But there was an overlap. The problem was the two gentlemen had actually gone and mapped the same rocks. And so what had happened is they had both included them in their own systems. And this was a bit of a problem, so that actually led to a 44-year-long argument. Essentially with people arguing, should these rocks be included in the Cambrian system or should these rocks be included in the Silurian system? And it wasn't settled until 1879 when Charles Lapworth came along and he said, I think you're being a bit stupid about this. How about we just take the rocks which are part of the overlap out of both the systems and put them into a system of their own, which we'll call the Ordovician system. So the Ordovician is actually part of the geologic timescale to stop an argument. That's the reason it exists. So essentially now you can see we now have the Cambrian system, the Ordovician system and the Silurian system, which you might also notice are the name of periods in the geologic timescale. Now obviously so each one of these systems is now a known package of rocks, and that means we also know their position in the stratigraphic system. So we know that the Cambrian's at the bottom, the Ordovician is on top of the Cambrian, and the Silurian is on top of the Ordovician. And the other thing is as well as looking at the rocks, they will have also been taking notes of the fossils which occurred in each of these systems as well. So before Sedgwick and Murchison were doing their thing in Wales, someone else had already been into the area of Devon in southwest England, and they had looked at the rocks down in Devon, and they had put them into a system which they called the Devonian. So at the time, the observations from the Devonian system were considered on a local scale, but once Sedgwick and Murchison's observations were published, it became clear pretty quickly that the Devonian sat above the Silurian. So you might notice now we have Cambrian, Ordovician, Silurian, Devonian, which are also periods in the geologic timescale. So once again, each one of these systems that's being defined is just a randomly selected packet of rocks from an area. So they also noticed that the rocks and fossils of the Devonian system were distinct from the older Silurian rocks and the younger coal-bearing rocks of the Carboniferous system, which was classified using the rocks of northern England. So now we have Cambrian, Ordovician, Silurian, Devonian, Carboniferous. And to finish it off, in 1841, Murchison travelled to western Russia and identified strata as Silurian, Devonian and Carboniferous. So what Murchison decided was, right, I've got these systems and I know the fossils which are in these systems. So what I'm going to do is I'm going to go as far away as I can from the United Kingdom. And at that time, obviously, travelling took time. So he went as far as he could, and as far as he could was Western Russia. And he looked at rocks in Western Russia and he was looking for the same fossils. And he found them. And so what that meant is he could then use those fossils to essentially correlate between the layers of rock in the United Kingdom and the layers of rock he was seeing in Russia. And that allowed him to say, right, these rocks were forming at approximately the same time. What he realised, though, while he was in Russia, was that there was still another package of rocks on top of the Carboniferous. And he called that package of rocks the Permian, after the Perm-Krai in Russia, where he identified them and mapped them. So now you can see we have the Cambrian, Ordovician, Silurian, Devonian, Carboniferous and Permian. So we now have all of the Paleozoic rocks, or should I say all of the Paleozoic accounted for. So earlier on, or around the same time, people had been also looking at the rocks of continental Europe. So in 1795, Alexander von Humboldt recognized a distinct sequence of limestones in the Jura Mountains in Switzerland, which he called Juracalc. And this sequence of rocks was later used to define the Jurassic system. In 1822, a man whose name I would get horribly wrong, so I'm not even going there, identified a sequence of chalk-dominated beds, and essentially he was looking at these beds. They were around Paris, I believe, and he essentially named that system the Cretaceous, because of course crater is chalk in Latin. And in 1834, Frederick von Alberti defined the Triassic system based on 3 very distinct rock layers which are found throughout Germany and northwestern Europe. And so once those systems had been identified, then they were put into the order, and it was realised they sat above the Paleozoic systems. And so once their order was worked out, it was Triassic, Jurassic, Cretaceous. So now we have Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous. So you can see we now have a very substantial part of the geologic timescale, don't we? And all that's happened is we've just had these early geologists going out, mapping sequences of rocks, working out where they fall in the sequence, and giving each of these packages of rocks a name, and its own distinct name. And so we can use those names to define that package of rocks. Now, the fossils in those rocks are a secondary consideration. We're focused mostly on the rocks right now because the main challenge was trying to work out where these rocks fall in the relative geologic time sequence. So what geologists were doing is they were using superposition and faunal succession to produce a composite geological column. And because this column is chronologically organised, in effect it is a relative geologic timescale. Now, the problem with rocks that are formed, well, were deposited before the Cambrian, is that they do not contain many fossils, and any fossils that are present are often extremely small or microscopic, so they're very difficult to see. And so this meant it was impossible to subdivide rocks which were older than the Cambrian. And so all of those rocks which were older than the Cambrian, all of them are mostly fossil-free, they put them into a group which they called the Precambrian. Okay, so now let's have a think about stratigraphic terminology. So we have a geologic timescale based on these packages of rocks, and over time we've also added fossils to that sequence to help us work out where the boundaries are. Because remember, most of the boundaries in the geologic timescale are based on the first or last appearance of one or more key fossils. However, one of the problems we have is that as many sedimentary rock bodies are time transgressive, or to put it away, they not only young upwards but also laterally. So if you remember, we were talking about Wolfer's Law, and we were discussing how if you follow a layer of rock, that layer of rock doesn't keep the same age all the way along. So if you're starting at a location, so let's say I'm starting at location X and I go west, well, the rock might be getting older in that direction. If I go back to location X and then decide to go east, well, in the opposite direction, it will be getting younger. So the age of a layer of rock will change laterally. So this is something we need to also take account of. So to get around this, geologists use terminology for 2 fundamentally different types of units. Those that are defined by their content, so the rocks themselves, and those which are essentially an expression of or related to geologic time. Okay, so these are our different groupings. This table is taken from the textbook once again. So what we can see is over here, we have units which are defined by their content. We have the lithostratigraphic units, they're based on the rocks. And we have the biostratigraphic units, those are defined using fossils. Then over here we have the units expressing or related to geologic time. We have the time-stratigraphic units, which you might notice down here we have systems. So these are the ones this is the set we've been talking about already, the ones that Murchison and co were coming up with. And over here, we actually have a different set of units which are called the time units. Now, these are the ones that you are familiar with from the geologic timescale: the eons, the eras, the periods, the epochs, and the ages. And I am just going to make this clear right now. Time stratigraphic units and time units, although they pretty much match up, they aren't perfect. So the systems and the periods are pretty much exactly the same thing, but when they start and finish is slightly different. They don't, match perfectly. Okay, so let's think about units defined by their content. So we're going to use the rocks only, and we're not going to consider any, we're not concerned about time in the slightest. So they are used to define a lithostratigraphic unit, which has a unifying feature which sets it apart from another lithostratigraphic unit. So what we'll do is we'll look at a layer of rock or a sequence of rocks, and we'll say, right, there's something about this sequence that sets it apart from the rocks below it and the rocks above it. And so I will use that, and I will put that sequence of rocks together. And the most basic unit of lithostratigraphic units is the formation. And the formation is, it can be just one layer of rock, or it can be several layers of rock, but the most important thing is that the formation has a mappable upper and lower boundary. So you know when the layer you know when the formation starts, and you know when the formation ends. So the term formation can also be applied to igneous and metamorphic rocks, so something like a sequence of basalt lava flows. However, it is mostly only used in reference to sedimentary rocks. So here's our sequence of rocks that we're looking at. So you can see here we have 9 layers. So at the bottom here we have a marine mudstone, then we have a marine limestone, then we have a marine sandstone. So these have all been forming in the ocean. Then on top of that we have a conglomerate which is of desert origin. We have a sandstone which is formed in the desert, and we have a layer of evaporites which have also formed in the desert. On top of that we have a greywacke which is of a fluvial origin, so it's river related. On top of that we have a mudstone which is also fluvial, so that's also been deposited due to rivers. And then on top of that we have a mudstone which represents a lacustrine or lake environment. So you can see we have a sequence of sedimentary rocks here. So what we're going to try and do is we're going to split these into some formations. And so we've got to kind of use our knowledge to link these rocks together somehow. So what we'll do is we'll call these bottom 3 layers formation number 1. So although they're different rock types, they all formed in the same environment. And so we'll lump them all together and we'll say, right, this is formation number 1. And formation number 1 is distinct from formation number 2, because formation number 1 formed in the oceans. Formation number 2 formed on dry land, and more accurately in a desert environment. So these are continental sedimentary rocks. So as you can see, they are distinct, and so we can use them to essentially, we can say, right, formation 1 is distinct from formation 2. And so obviously we can use this as our mappable upper boundary for formation 1. In terms of these 3 rocks up here, well, they're all associated with freshwater processes. So we have 2 formed by rivers, and we have 1 formed by a lake. And so we can lump those 3 layers together, and we can call them formation number 3, because once again they are distinct from formation 2. Formation 2 formed in a desert environment, hot and dry, whereas formation 3 is associated with the movement and deposition of sediments by fresh water. So clearly a completely different environment. So we can use those basic principles to split up our sequence of rocks, in this case into 3 formations. Now there are also other units that are present when looking at these lithostratigraphic units. So the unit below the formation, so a smaller unit, would be a member. So a member is essentially a smaller unit, so it's a subunit of a formation, and in this case what you can see is we've split up formation number 3. So what we realise is these 2 lower layers, well, they're related to river processes, so they are evolution, from an evolution point of view, very similar to each other, and so we can put them together and we can say, right, well, they're a member. And as you can see, we've excluded this upper layer because it hasn't been formed by river processes. It's part of a lake sedimentary process. Now the other thing we can do is we can then also bundle formations together to make an even bigger unit, which is called a group. And so what you'll notice is that this layer, that layer, that layer, that layer, that layer, and that layer are all of continental origin. They all formed on dry land. And so what we can do is we can put them together, and we can put them together to form a group. So what you'll notice is we can bundle rocks together to form larger and larger packages of rocks. So formations are subdivided into members. So members are normally 2 or more layers of rock thick. And then we have beds. A bed is typically just a single layer of rock. So the smallest lithostratigraphic unit is a bed, then a member, then a formation. We can combine formations together to make a larger unit, which is called a group. And then if we package together 2 or more groups, we end up with a supergroup. And so once again, going from smallest to largest, it's bed, member, system, sorry, let's try that one again, shall we? Bed, member, formation, group, supergroup. The most important thing to remember is that everything from a bed all the way up to a supergroup must have a defined upper and lower margin. You must know exactly when the unit starts and stops. So the other type of unit that's concerned with the contents of the rock is a biostratigraphic unit. Now we're going to cover these in greater detail in a few slides time, but we're just going to very, very briefly run over the basic idea. So in terms of a biostratigraphic unit, what you're doing is you're splitting up a sequence of rocks based exclusively on the fossils. You don't care about the rocks at all. You're just in it for the fossils. So as you can see over here, we have a sequence of 5 rocks, and within this sequence we have 2 different fossils. We have these white circles and we have these yellow stars. And so what we can do is we can use these organisms to define a biozone. So a biozone is an area or region of the sequence where we have 1 or more fossils occurring. So in this case, I've split the sequence up into 2 distinct biozones. Biozone 1 is represented by it begins where the first white circle first appears, and it ends when the final white circle fossil appears. From this point on, you can see they're not there anymore. So this is the start of the biozone, this is the end of the biozone. Biozone number 2 starts here where we have the first appearance of the yellow star fossil, and it ends up here where we have the last appearance of the yellow star fossil. The one thing you'll notice is the biozones, where they start and finish, do not correspond to where the layers of rock start and finish, because we don't care about the rocks. We are just focused on the fossils. So biozones are concerned with the fossils. Lithostratigraphic units are concerned just with the rocks. You don't care about the fossils at all. So now we need to think about the units which are expressing or related to geologic time. And I'm going to be honest, this is a bit more complicated. So the time-stratigraphic units are also referred to as chronostratigraphic units. And they define a rock unit forming during a particular interval in geologic time. Now this interval can be defined by either fossils, or it can be defined by absolute ages, which we get from radiometric dating. So the most common time stratigraphic unit is the system, okay, and we've already spoken about them. These are based on these packages of rocks. And so what's happened is, just once again, geologists have gone out, they've gone to an area, they've mapped all the rocks in that area, and they've just gone, right, I will call all these rocks, I'll put them together into one package, which I will call the Cambrian system. So these systems are based on the stratotype, and that's the sequence of rocks that we see in the original area. So for the Cambrian system, the stratotype is the rocks of northern Wales. For the Silurian system, the stratotype is the rocks of southern Wales. So the systems are recognised beyond their stratotype areas by their fossil contents. Because think about it, the rocks you're getting in southern Wales are not going to be the same rocks that were forming at the same time in Russia. Okay, they would have been different locations with different environments, and as such you would get different rocks deposited. So you're not going to see the same rocks at both locations. What you are going to see though is possibly, if you're lucky, the same fossils, and that's going to allow you to link those rocks together. So these time stratigraphic units are based on the rocks, but when we're trying to link them together over large distances, we have to use the fossils because the rocks obviously change. And this process is, why Impey Murchison could go to Russia and identify Cambrian to Carboniferous age rocks, by comparing them to the stratotypes from the UK, or more accurately, the fossils found within the stratotypes from the United Kingdom. So the geologic timescale is also split into time units. So a time unit is a portion of the geologic timescale with a set upper and lower limit. And the most common unit, the one we've spoken about in the past, is of course the period. Now there are also larger units, the eras and the eons, and there are smaller units, the epochs and the ages. And we know that the boundaries between these ages, epochs, periods, eras and eons are based on fossils in most cases. So each of these boundaries is based on the first and last appearance of certain key fossils. So you might notice that there's a difference, isn't there? We have the time stratigraphic units. They were based on the packages of rocks, and then just by looking at the fossils present in that package of rocks, that's how we managed to link up these time stratigraphic units over large distances. The fossils were initially a secondary consideration. In the case of time units, we are using something. So we're using the fossils, or we're using an absolute age date to actually say, right, this is where I start, this is where I end, based on when this fossil first or last appears. So the time stratigraphic units are material bodies of rock that occupy positions in a sequence of strata. So the Devonian system, it's a bundle of rocks, and we know where it sits relative to the other systems in the geologic timescale. We care only. Yeah, that's a really bad sentence. I don't know what was going on there. We're only really concerned with the package of rocks and its position in the stratigraphic sequence. As I said, the fossils were a secondary consideration. And so systems are often split into lower, middle and upper parts. So you would have the lower Devonian, the middle Devonian and the upper Devonian. Now the time units, which are different, they refer only to time. Now remember, this is either relative time based on the principle of faunal succession, or it's absolute time based on radiometric dating. So time units are split into early, middle and late subdivisions. So you'll have the early Devonian, middle Devonian and late Devonian. So you might notice that you're using the same kinds of terminology, but when fossils appear will not always match perfectly with when a layer of rock starts. And so this means that that where the time stratigraphic unit begins may not be the same location where the time unit begins. So if we just go back a few slides to this picture here, imagine this is our sequence for, let's say, the Devonian. Okay, so the Devonian system starts here and the Devonian system ends here. Okay, so this is going to be our time stratigraphic unit. It's defined by the rocks. Now in terms of the time units, we are using either the fossils to produce a relative age, or we are using absolute age dating based on radiometric dating. So in this case, what we can see that, well, if we were to say that the Devonian, in terms of the time unit, begins when we first see the white circle fossil appear, well, this is when the Devonian is going to begin in terms of time units. So the Devonian begins here if we're thinking about time stratigraphic units, but it begins here if we're thinking about time units. Now, most of the time, the boundaries will match up almost perfectly, but not every single time. So it means that the time stratigraphic units and the time units don't always match up perfectly. So just be aware of that. They are super close, but it's not a 100% perfect correlation. So geologists have attempted to synchronize the time stratigraphic and time units whenever possible. However, they don't always align perfectly. So here we go again. So we have our units which are defined by the contents. So lithostratigraphic units are focused on the rocks. So that's beds, members, formations, groups, and supergroups. Essentially becoming, the higher you go in the list, the more layers of rock you have in your package. Then we have the biostratigraphic units, and those are defined using biozones, which are based on fossils. So you're not really worried about what the rock is made of, you're only concerned with the fossils. But in both cases, we are looking at what's in the rock. In terms of the units related to time, we have the time stratigraphic units, going from smallest to largest, stage, series, system, erotherm, eontherm. And then we have the time units, age, epoch, period, era, eon. And they match up almost perfectly, but not every time. So they are considered to be distinct from one another. So this is a good place to stop. So once again, stop the video, get up, have a walk around, go in a glass of water, sit down, relax for a few minutes, and then come back for part 3, please.